The USS Nautilus was the world's first operational nuclear-powered submarine, a technological triumph of the early Cold War era. Authorized by Congress in 1951, just 4 years later, on January 17, 1955, under Commander Eugene P. Dennis Wilkinson, Nautilus cast off her lines and sent the historic message, "Underway on nuclear power." Powered by an onboard nuclear reactor, Nautilus could remain submerged far longer and travel faster underwater than any diesel-electric sub before her. This breakthrough fulfilled a long-held vision of a true submarine, a vessel that could operate continuously beneath the waves, free from the need to surface frequently. The development of Nautilus required visionary leadership, new technology, and solutions to unprecedented engineering challenges. This video provides a structured overview of how Admiral Hyman G. Rickover and his team turned the nuclear submarine from concept into reality, covering the historical context, strategic motivations, key technical decisions, and the roles of major figures and contractors, including a young Lieutenant Jimmy Carter. World War II had demonstrated the tremendous impact of submarines in naval warfare, but also highlighted the limitations of the diesel-electric submarines of the era. Conventional subs had to surface or snorkel regularly to recharge batteries, limiting their stealth and endurance. Underwater speed was also very limited. For example, the U.S. Navy's most advanced late 1940s diesel subs, the Tang class, could make about 17 knots submerged for only about an hour before exhausting battery power. A 1946 report by Naval Research Laboratory scientist Ross Gunn and physicist Philip Abelson suggested that an atomic-powered submarine could achieve 26 to 30 knots submerged and operate for years without refueling. Early in the Cold War, both the U.S. and other nations recognized that a submarine with a new power source would confer a massive strategic advantage. The U.S. Navy explored various alternatives, including closed-cycle engines and high-test peroxide system, but these offered only incremental improvements in underwater performance. Abelson even speculated that within a decade, radically redesigned nuclear subs might reach 40 to 60 knots undersea, far beyond any diesel sub's capability. Such performance would render obsolete the anti-submarine tactics of World War II, which assumed submarines must surface often. The strategic motivations for a nuclear submarine program were therefore clear: to create a truly stealthy, long-range undersea vessel that could outrun and outlast any conventional submarine. This was not only crucial for anti-shipping or attack roles, but it also laid the groundwork for future missions like polar under-ice transit and, eventually, nuclear deterrence with submarine-launched missiles. By the late 1940s, the United States had a strong lead in nuclear technology from the Manhattan Project, and visionary thinkers in both the scientific community and the Navy pushed to leverage that lead for naval propulsion. In 1946, as the U.S. established the Atomic Energy Commission, abbreviated as AAC, to oversee nuclear research, the Navy assigned a small group of officers to learn about reactor technology at Oak Ridge, Tennessee. Among them was Captain Hyman G. Rickover, a former submarine officer and engineering specialist who would become the driving force behind Nautilus. Admiral Hyman G. Rickover, who was a captain in the late 1940s, is often called the father of the nuclear navy, and for good reason. Rickover's personal vision, relentless drive, and deft navigation of bureaucracy were pivotal in launching the nuclear propulsion program. In mid-1946, Rickover was sent to Oak Ridge as part of a Navy contingent working on an experimental reactor project. There, he became convinced that nuclear-powered ships, especially submarines, were not only feasible but essential to the Navy's future. His immediate supervisors were skeptical of the idea, initially reassigning him to other duties, but Rickover bypassed the chain of command and took his case directly to the Chief of Naval Operations, Fleet Admiral Chester Nimitz. Nimitz, himself a former submariner, supported the concept. Backed by Nimitz and Secretary of the Navy Dan Kimball, the Navy in 1948 to 49 created a dedicated nuclear power branch within the Bureau of Ships, sometime referred to as Bu-Ships, and installed Rickover as its head. Simultaneously, the AEC appointed Rickover as director of its new Naval Reactors branch in its Reactor Development Division. By 1949, Rickover wore two hats, one as a Navy captain in charge of nuclear propulsion in Bu-Ships, and one as an AEC official overseeing naval reactor development. This dual authority was unprecedented, but proved crucial. It allowed Rickover to coordinate and control both the military requirements and the nuclear engineering aspects of the project, cutting through interagency red tape. Rickover proved to be an extraordinary leader of this program. He insisted on total responsibility and accountability, famously micromanaging everything from high-level design reviews down to the selection of personnel and contractors. In the words of a 1952 Navy Award citation, Captain Rickover, more than any other individual, is responsible for the rapid development of the nuclear ship program. His efforts have led to the laying of the keel of the world's first nuclear-powered ship well in advance of its original schedule. That first keel of Nautilus was laid in June 1952, just a few years after the program began, reflecting Rickover's unceasing drive and energy, as noted in the same citation. Part of Rickover's leadership strategy was to secure the best talent and hold them to exacting standards. He personally interviewed every officer candidate for the nuclear fleet, establishing a rigorous vetting process that became legend in the Navy. Under Rickover's direction, the Navy and AEC worked in tandem to turn nuclear propulsion from theory into practice. He leveraged high-level support to obtain funding and priority. In July 1951, Congress formally authorized the construction of a nuclear-powered submarine, then known only as Project K, or the atomic-powered submarine. Rickover also ensured that the project had the freedom to depart from Navy norms when necessary. For example, instead of assigning construction to a Navy shipyard under traditional bureaucracy, Rickover opted to use a private contractor, Electric Boat Company, because it could more readily accept direct oversight from his Naval Reactors Group and operate with flexibility. Throughout the project, Rickover's insistence on safety, reliability, and technical rigor set the tone. He demanded exhaustive testing of components, quality control in manufacturing, and thorough training for the crew. The fact that the U.S. Navy has never had a nuclear reactor accident is often attributed to the culture of excellence and strict standards Rickover instilled from the beginning. At the heart of Nautilus was a revolutionary power plant, a tiny nuclear reactor capable of propelling a submarine. In the late 1940s, no reactor in the world had ever been used to drive a ship, so choosing the right reactor design was a critical decision. Early on, the Naval Reactors team considered three different reactor concepts that might meet the Navy's needs. First was a gas-cooled reactor. This design, inspired by the wartime Daniels Pile project, would use a gas, like helium, to transfer heat from the reactor to steam generators. While feasible in principle, gas is a poor coolant in terms of heat capacity. Analyses showed a gas-cooled reactor would need to be relatively large, with bulky heat exchangers, to produce the required power. Given the materials available in the 1940s, a compact high-performance gas reactor was out of reach. The size and space requirements simply wouldn't fit in a submarine hull. This concept was set aside as impractical for the first-generation submarine. Second, a liquid metal-cooled reactor, LMR. A more promising option was to use a liquid metal, such as molten sodium or a sodium-potassium alloy, as the coolant. Liquid metal conducts heat extremely well, allowing for a very high power density. A smaller reactor could produce more power. The liquid metal design the Navy examined was an intermediate spectrum reactor, neutrons at energies between fast and thermal, that could even breed fuel, an idea pursued by scientists at General Electric's Knowles Atomic Power Laboratory. The LMR offered advantages: higher temperature output for efficient turbines and a compact core moderated only slightly, yielding more neutrons per fission. However, the drawbacks were formidable. Sodium is highly reactive. Any leak or contact with air or water can cause fires or explosions, so the entire system must be absolutely leak-proof. The metallurgy was uncertain. Piping, pumps, and valves all would face corrosion and sealing challenges with hot liquid sodium. Every piece of equipment in an LMR plant, pumps, heat exchangers, instrumentation, would essentially need to be invented from scratch to handle sodium's properties. Because of these unknowns, the liquid metal reactor was recognized as high risk. Rickover and the AEC viewed it as a backup in case the primary approach ran into trouble. They did initiate an LMR project a bit later. This became the reactor for the second nuclear sub, USS Seawolf, but it was the fallback option rather than the main plan. The third option, shortened as PWR, was a light water-cooled and moderated reactor, the design that ultimately powered Nautilus. In a PWR, ordinary water serves as both coolant and neutron moderator. Water had several points in its favor. It provided a nice thermal neutron spectrum, good for efficiency with enriched uranium fuel, and decent heat transfer capacity, so a water-cooled core could be made compact. If the reactor used very highly enriched uranium, the core could be physically small while still producing significant power. A high-pressure primary circuit would be needed to prevent the water from boiling, keeping it liquid up to high temperatures. This meant the steam produced for the turbines would be lower pressure and lower temperature than in a conventional fossil fuel plant, which in turn meant slightly lower thermal efficiency and the need for specially designed turbines. But crucially, the PWR's challenges, high-pressure vessel, pumps, seals, and heat exchangers, were engineering problems that could be tackled with known technology and materials given sufficient development. Water is chemically benign in a marine environment. Leaks would just be water, not combustible sodium. And unlike the exotic coolant systems needed for an LMR, a pressurized water system could draw on decades of experience in boilers, pumps, and piping from conventional power plants. All these factors made the PWR concept appear more attainable and safer for a first-of-a-kind submarine reactor. By 1948-49, after extensive study, the Navy and AEC decided to make the pressurized water reactor the primary path for the submarine program. The first project was codenamed the Submarine Thermal Reactor, STR, later known as the S1W and S2WPWR. This decision did not eliminate the other approaches entirely. Work on the sodium-cooled reactor continued as an alternate, Submarine Intermediate Reactor, SIR, at Knowles Laboratory, and eventually led to an operational sodium-cooled plant in Seawolf. But Rickover's team placed primary emphasis on the water-cooled reactor concept for Nautilus. This choice proved wise. While Nautilus's PWR performed well, Seawolf's sodium-cooled reactor, which went to sea in 1957, suffered reliability issues. The liquid sodium system's complexity led to debilitating maintenance problems. And in 1959, the Navy removed Seawolf's sodium reactor and replaced it with a PWR similar to Nautilus's, designated S2WA. That marked the end of the liquid metal coolant experiment in U.S. subs. The simpler and more mature PWR technology had won out decisively. The PWR design pioneered for Nautilus not only became the standard for all subsequent U.S. nuclear submarines, it also was adapted into the first commercial nuclear power plant in the USS, Shippingport, operational 1957, and remains the dominant reactor type in naval and civilian use to this day. Building a nuclear submarine in the early 1950s was a crash program in innovation. The fundamental principles of a naval reactor had been worked out on paper, but now they had to be turned into practical hardware that would operate safely and reliably in a cramped submarine hull. Key engineering challenges included reactor fuel development, radiation shielding, heat exchanger, and turbine design, and overall integration of the reactor into a submarine environment. The project essentially required creating a new technology discipline from scratch, as Rickover later noted. Nuclear naval engineering did not exist before this effort. One major concern was nuclear fuel and materials. The reactor core had to be small, yet produce a high power density and last for years without replacement. This demanded highly enriched uranium fuel to pack maximum fission power in minimum volume and new types of fuel elements. Equally important, the metal cladding and structural materials in the core had to withstand intense radiation and high temperatures without degrading. Early on, the Naval Reactors Program launched a nationwide effort to develop suitable fuel elements. Argonne, Oak Ridge, Brookhaven, and Ames Laboratories, along with industrial partners like Battelle Memorial Institute, MIT, and the Sylvania Corporation, all contributed to fuel metallurgy research. Prototype fuel rods were irradiated in reactors. Even a Hanford production reactor was used to test samples to see how they held up. This broad R&D program eventually produced a robust uranium fuel alloy and cladding that exceeded the initial life requirements, a success that was critical for Nautilus to achieve long endurance at sea. Another challenge was radiation shielding. The reactor would emit potent radiation, neutrons, and gamma rays that could be deadly to the crew and could also damage equipment. The shielding around the reactor was expected to be the single largest weight item in the submarine's design. To minimize that weight, the reactor needed to be as compact as possible, hence the use of highly enriched fuel. Even so, designing adequate shielding was a complex task. It had to reduce dose rates to safe levels in crew spaces, maintain the submarine's balance and center of gravity, and not overburden the hull with weight. Naval reactors engineers used calculations and experiments to determine shielding thicknesses and materials like lead, water, polyethylene, and steel combinations. They also took into account the shadow shield effect of placing the reactor low in the hull so that the ocean could act as additional radiation shielding in certain directions. In fact, when they built the prototype plant on land, see below, they surrounded the hull section with a simulated sea, essentially a tank of water, to mimic how water would scatter and absorb neutrons, thus testing shielding effectiveness in conditions analogous to an actual sub. A critical piece of the engineering puzzle was the steam plant and propulsion machinery that the reactor would drive. Unlike a diesel-electric sub, which used batteries and electric motors for submerged propulsion, Nautilus would use a nuclear heat source to produce steam and turn turbines. This meant designing steam generators, heat exchangers, turbogenerators, or turbomechanical drives, condensers, and pumps suitable for a submarine. The use of pressurized water cooling imposed some limitations. The steam from the STR Mark I reactor was at lower pressure than contemporary fossil fuel power plants, so the team needed turbines that could efficiently work with lower pressure saturated steam. The solution was effectively to design a custom turbo gear set for the submarine, borrowing from past naval engineering. As one account noted, industry turned its design requirements back 20 years to an earlier era of lower pressure turbines, but then updated those designs with modern materials and techniques. Every component had to be compact and quiet. Even the main coolant pumps were a novel design. Rickover's team and Westinghouse developed canned rotor pumps, a type of pump with a sealed motor, to circulate reactor coolant with high reliability and no shaft seals that might leak. Perhaps the most daunting challenge was simply uncertainty. So much was untested. Would the reactor behave stably under the motion of a ship? Would nuclear reactions unexpectedly cause the water coolant to break down chemically? For example, scientists worried about radiolysis of water in the reactor, splitting water into hydrogen and oxygen under radiation. Experiments at Argona and Oak Ridge confirmed that while some gas would be produced, it would be a manageable amount that recombined or could be removed and would not threaten safe operation. Each potential showstopper had to be investigated through analysis or experiment, often in parallel with construction. To mitigate risk, the Naval Reactors Program pursued a strategy of building a prototype reactor plant on land before the actual ship's plant was installed. This prototype, called Esther Mark I, was constructed at the AEC's National Reactor Testing Station in Arco, Idaho. Starting in 1950, Westinghouse, which had been contracted in 1948 to design the reactor, and Electric Boat, the submarine builder, collaborated to erect a full-size reactor and engine room inside a steel submarine-like hull section out in the Idaho desert. The idea was to make the prototype as ship-like as possible. Same layout, same equipment, same cramped spacing. If problems were discovered, it would be far easier to fix them in this on-land prototype than if they only became apparent after the submarine was built. Rickover's team even anticipated the effect of surrounding water on the reactor. Since water reflects neutrons, the absence of an ocean in Idaho could influence reactor physics. That was the reason for the large water tank around the prototype hull, a simulated sea, to mimic the moderating effect of water around a submerged sub. Construction of the prototype plant began in 1950 and was completed by early 1953. In March 1953, the Idaho reactor was brought to criticality. Self-sustaining nuclear chain reaction started, and by May 1953 it produced full power, a major milestone showing that a submarine PWR could indeed work. Notably, the Idaho prototype's success came after the submarine had already been authorized, and even after keel laying. The project deliberately overlapped these phases to save time, an approach that carried some risk but ultimately paid off. Running in parallel to the reactor development was the submarine hull design and construction. Initially, planners considered making the nuclear sub about the same size as existing fleet submarines, roughly 18 feet in diameter and approximately 300 feet long, with a displacement on the order of 2,000 tons. As the reactor and shielding needs became clearer, the design grew larger. In the end, Nautilus measured 320 feet in length, 28 feet in beam, and about 4,100 tons submerged displacement. This was significantly bigger than the diesel-electric subs of the day. The extra size accommodated the reactor compartment amidships and the heavy shielding around it. Electric Boat, EB, in Groton, Connecticut, was chosen to build Nautilus in part because as a private company it could be more directly tasked and controlled by Rickover's team than a Navy yard bound by traditional hierarchy. The Navy's Portsmouth Naval Shipyard, though experienced in submarine construction, was not used because it was committed to the standard buship's management chain, and there was internal resistance to the nuclear upstart. Thus, EB became the primary shipbuilder, working closely with Naval Reactors and Westinghouse. In a unique arrangement, EB's on-site Navy supervisor reported both to buship's for the conventional aspects and to Rickover for the nuclear aspects, effectively satisfying two masters. Construction formally began when President Harry S. Truman traveled to Groton to lay the keel of Nautilus on June 14, 1952. By that time, many design details were still being finalized, but the project pressed forward under tight timelines. To avoid costly errors, EB built a full-scale wooden mock-up of sections of the submarine on the shipyard premises. Engineers and shipfitters used this mock-up to verify the fit of every pipe, cable, and piece of machinery in the crowded interior before the real hardware was installed in the hull. This attention to detail paid off in reducing rework. Additionally, critical components of the propulsion plant were tested for shock and vibration. The Navy took an unused submarine hull, the incomplete hull of USS ULUA, a World War II-era boat, and installed prototype machinery in it for shock testing in Chesapeake Bay. They subjected equipment to underwater explosive charges to ensure the reactor and steam plant components could withstand shocks equivalent to depth charge attacks. All of this was unprecedented testing for an unprecedented ship. By late 1953, lessons from the Idaho prototype were being fed back into the ship under construction. Fortunately, no major redesign was needed. The prototype's performance validated the basic design. The hull of Nautilus took shape on the ways at EB, and on January 21, 1954, the submarine was ready to launch. In a celebratory ceremony, First Lady Mamie Eisenhower christened Nautilus by breaking a bottle of champagne across its bow, and the submarine slid down into the Thames River at Groton. This launch marked the beginning of a new era in naval history. 8 months after launch, on September 30, 1954, Nautilus was officially commissioned into the U.S. Navy, with Commander Eugene Wilkinson in command. Final reactor and ship trials continued pierside until the power plant and crew were ready. Then came the historic first sailing. On January 17, 1955, Nautilus cast off and signaled her famous message, "Underway on nuclear power." The submarine performed as hoped. In her first year, Nautilus broke all submerged endurance and speed records. In one early shakedown cruise, she steamed submerged from New London to Puerto Rico, 1,381 miles in 84 hours, at an average speed of about 16 knots. This was longer and faster than any submarine had ever traveled underwater before. The transformative impact of her capabilities soon became evident. Exercises showed that World War II anti-submarine tactics, which assumed a sub would surface or snorkel regularly, were useless against a vessel that could stay down for days at high speed. As one analysis noted, the nuclear submarine revolutionized propulsion capability and opened up strategic and tactical options previously only dreamed of. It's worth noting that Nautilus's design was not yet fully optimized as later submarines would be. Her hull was essentially a stretched version of a conventional submarine hull form. She still had a long, narrow bow and deck guns in her early configuration, features carried over from diesel boats. As operational experience grew, the Navy learned from Nautilus's limitations in design and construction. For example, at very high submerged speeds, Nautilus experienced stability issues and noise, prompting improved hydrodynamic designs. By the mid to late 1950s, the Navy developed the USS Albacore experimental sub with a streamlined teardrop hull, and this was combined with nuclear propulsion in the Skipjack class, commissioned 1959, to achieve even greater performance. Nonetheless, Nautilus provided the invaluable stepping stone. She proved the concept beyond any doubt, and every subsequent U.S. submarine would be nuclear-powered. The U.S. Navy rapidly de-emphasized diesel subs once Nautilus showed what was possible. Within a few years, an all-nuclear-powered submarine force became the goal.